All right, ladies and gentlemen, what we're going to be looking at into this video is kind of a follow-up to what we had seen in the previous one about graphing rational or graphing exponential functions, I should say. What we saw when we were graphing exponential functions is we said, okay, we have some function. Oops, let me get my pen going here. It's not wanting to work. Okay, so we have some function where we say whatever the base is, we raise it to the x power. And we identified certain key points. We said 0 and 1. We identified 1 and whatever the value of the base is. And we identified -1 and the reciprocal of the base. And we said, well, if we can identify any of those 3 points, we can graph any function, because from there we can just do some basic transformations and see whatever the function gives us is. Well, when we enter the realm of exponential functions, we start coming upon a number that has been designated e. E doesn't exactly stand for anything, just like the symbol pi doesn't exactly represent anything. It's just the Greek letter pi, so that's why we call it that. Well, here E is a naturally occurring number that we would classify as a transcendental number because it is an irrational number that just never kind of repeats itself. So this is one of the few types of transcendental numbers that we occur or that we're going to see in our units of study. Well, E is a very common number that is used in financial math, whether it's an exponential function or a logarithmic function. E is a very common base that we're going to be seeing in this unit of study. So because of its unique nature, I wanted to make a separate video explaining what they are. So here you see a basic kind of equation saying that this is how E was derived. We're saying, okay, if I say 1 plus 1 over whatever my variable happens to be, and I raise that to the same variable, uh, ultimately, as n approaches a larger and larger number, approaching infinity, we come up to this 2.718 blah, blah, blah number. And generally speaking, when we are thinking about E, we kind of just round it to the first decimal place. We just say 2.7. You could round it out to 2.718 if you wanted to be a little bit more accurate when you're writing down your answers, but every calculator that you're going to be working with, graphing scientific, just like it has a button on there that represents pi, there will be a button on there that will represent E as well. So you don't have to worry about writing out the entire decimal value. So here, what we're going to be talking about is how do you graph an exponential function when the base is E, because uh, it looks like something different than what we're used to seeing, because usually we see a number that represents our base, 5, 7, -1, 1/2, whatever the case is, but E is still just a number. So we treat it just like any other exponential function. So out of our 3 basic points, where I say 0, 1, 1 in the base, and -1 in the reciprocal of the base, we get 0, 1, 1 in E, and -1 and 1 over E. So the way that we would kind of look at this as far as, well, how are we going to plot our points? 0, 1, obviously, 1 and 2.7 to approximate E, and -1 and the reciprocal, if I say 1 divided by E, that gives me about 0.4. So those would be the decimal values that will look for the basic values or the basic coordinates for E. So when we graph it, we have a point at 0, 1, 1, and about 2.7. So we'll just approximate here, and then -1 and about 0.4. So again, we just approximate there. And it's going to follow the same pattern that every basic exponential function has, meaning that it's going to, at a certain point, grow super, super fast but it is also, as it heads towards negative infinity on the x-axis, we will approach a horizontal asymptote at y is equal to 0, or whatever vertical transformation that we wind up doing on it. So that's essentially how we're going to wind up graphing that function, and the same transformations that we would apply to any other exponential function will be applied to e as well. So let's take a look at this one here. The basic function, the base function is just y is equal to e to the x power, which gives us the points 0, 1, 1, and about 2.7 to approximate e, and negative 1 and 0.4 to approximate the reciprocal of e. Looking at the transformations here, we have e to the x plus 2 power. Well, that plus 2, that is indicating a horizontal translation. So we're going to, where it says x plus 2, that says move to the left 2 spaces. And the minus 3 says to shift down 3 spaces. So the side-to-side stuff, again, that's going to affect the x numbers of our function. So I'm going to take all of my x numbers and I'm going to subtract that by 2. Okay, so if I say, looking at the first coordinate 0, 1, if I subtract the x coordinate 0 by 2, I get negative 2. And all I'm going to do is subtract 2 from all of the x coordinates. So the next one, 1, says 1 minus 2 would give me negative 1 for the x coordinate here. And then the last one will give me negative 3 when I shift that one 2 spaces to the left. So the shifting down 3, that says subtract 3 from all of the y coordinates of the base function. So in the first point, I'll get negative 2. In the second point, I will get about 0.3 negative, and I will get about 2.6 negative for the third point. So if we plot our parent function, we have 0, 1, we have 1 and about 2.7, and negative 1 and about 0.4. So let's just go ahead and plot the points just like what that we calculated using our transformations, and then we can visually see that we take the parent points and move them 2 to the left and 3 down. So we're going to be at negative 2, and let me see if I can pick a different color here that will show up on the graph. So we're going to say negative 2 and negative 2. So here's a point here. Negative 1 and negative 0.3 would be kind of about right there. And negative 3 and negative 2.6 would kind of put me somewhere around here. And that the minus 3 of the function, that says that the horizontal asymptote of this function is going to be at y is equal to negative 3. So my horizontal asymptote looks right there, and so it matches up pretty much with what we expect to see. So we're going to follow the horizontal asymptote down or across, and then there is the overall function. Just kind of looking at the points that we have from the parent function at 0, 1, if I go 2 spaces to the left and 3 spaces down, that is the other way that we could figure out the points of the transformed function, is just plot the points that we know from the base function and do the transformation on the graph. However, whichever way works, actually adding and subtracting and multiplying with the transformations that we have, or graphing the basic points and doing it that way. So I just want to make sure you guys see every way that you can do it, because there is more than one way that you can do it. So here, the base function in this case is just going to be y is equal to e to the x power again, which will give us 0, 1, 1, 2.7, and negative 1, and 0.4. So here we actually have 3 transformations. The negative 2 says to reflect, that's going to reflect it over the x-axis, and it's going to give us a vertical stretch two times. So we're going to kind of pull it upwards two times from what we would normally do. Okay. The other transformation that we have, the plus 2 at the end, that just says to shift up two spaces. All right. So let's apply our transformations here. And well, before I do that, let me go ahead and plot the basic points. 0, 1, 1 and about 2.7, and negative 1 and about 0.4. And now let's look at the transformed functions. So let's look at what the negative 2 does, the reflection and the vertical stretch. Okay. Well, the negative 2, basically what that's going to tell you to do, because we're reflecting over the x-axis, that means we have to multiply all of the y values by a negative 1, and then we're going to move all of those two spaces up. Okay, the plus 2, and the 2 of the negative 2 component says, well, we're also going to stretch them vertically. Now, all of the transformations that we see in this particular function are affecting a vertical something. We're not doing any horizontal translations at all. We don't have any side-to-side shift. We're not reflecting it over the y-axis. We're not stretching it horizontally. Everything here is being affected to the up and down numbers, to the y numbers. So the negative of the negative 2x, or negative 2 times e, that says we're going to reflect it over the x-axis, so that means an up and down movement. The 2 says we're going to stretch it up and down 2 times. And the plus 2 says, again, we're going to move it up and down 2 times. So there's no side-to-side movement here, so none of the x coordinates of my base function in this case are going to change. So what I'll do is I will multiply all of the y coordinates by negative 2 and then add 2 to whatever that number is, because we will kind of apply the transformations the same way that we would do our normal order of operations. So we multiply first, then we add. Okay, so if I say negative 2 times 1, that's going to give me negative 2, and if I add 2 to that, it's going to give me 0. So now let's look at the 2.7. If I multiply negative 2 or 2.7 by negative 2, and then I add 2 to that number, that's going to give me about negative 3.4. And then the positive 0.4 for the last coordinate, same thing, multiply that by negative 2 and then add 2, I'm going to get about 1.2. So here are the points of the transformed function. So we're going to go ahead and plot those points. We have something here, 1 and negative 3.4, so 1 and negative 3.4 will kind of put me about right here, and negative 1 and a positive 1.2 will kind of put me about right there. And of course, this plus 2 says my horizontal asymptote for this function is going to be at y is equal to a positive 2. So you can see, because now from the parent function that curves up as we go from left to right, because we reflected across the x-axis, now it's going to curve down as we go from left to right. And the points are further apart up and down because we stretched it by 2. So the function is going to follow the horizontal asymptote, hit this point, go through that point, and then follow down there. And here is our happy little function. And that's essentially it. Again, it's just a normal exponential function, except it has a different number for the base than what you may used to be seeing. It's a transcendental number e rather than 5 or 1/2 or -2. So we've treated the same way that we do any other transfer or exponential function when we graph it, and from there we just keep doing what we normally do. So I hope you've been paying good attention. If you have any questions, make sure you have them written down and bring them to me when you come see me in class. And hope to see you guys soon. Take care.